Okay, welcome to the class once more. Since we've talked about the basic principles of errors and formulas and how to deal with um, figures, data in basic chemistry, move on to historical development of atomic theories. But this should be the part one of it because after this, under this, we're talking about law of conservation of mass, which is similar to law of conservation of energy, but it's somewhat different. But just changed semantics. Law of conservation of mass, law of constant composition, Dalton's atomic theory, which was the first atomic theory learnt. Cathode rays, that's negatively charged particles, electrons. We talk about Thomson's mass to charge experiment, which he found the value for the mass to charge ratio. Talk about the protons. We talk about Millikan's experiment also, the all drop experiment. We talk about Thomson's atom model. How can we describe the Thomson's atom model? We talk about Rutherford's alpha scattering experiment and its shortcomings. Also, we'll talk about the Bohr's model, limitations of the classical theory, introduction to the quantum theory of the atom. Talk about the limitations of classical theory. Okay, we'll talk about atoms, atomic mass, atomic number, mass number, and isotopes. So let's get to work. Okay, law of the conservation of mass. Um, Okay, what does it say? It says the total mass of substances present after a chemical reaction is the same as the total mass of substances before the reaction. Total mass of substances present before a chemical reaction is equal to the total mass of substances before the reaction. After the reaction and before the reaction, they are both equal. Let me give it's just like saying the law is saying the mass is conserved during the chemical reaction. We all know the law of conservation of energy. Like energy is neither created nor destroyed, but converted from one form to another. That means if you add the energy before the reaction and the energy is produced after the reaction, or the energy is splitted in different forms after the reaction, you will get it. Just like having total energy equals to PE plus KE. This is not part of it, just an illustration. No, potential energy is a mass change to gravity plus half mv squared. Okay, we know this one. So it's just the same thing. The total energy here is equal to the total energy of the potential and the kinetic energy. Okay. So law of conservation of energy and law of conservation of mass is saying almost the same thing, just the energy involved and the mass involved. No, mass is not the same thing as energy. Okay, energy is the ability to do work, well, mass is the what composed the substance, the composition of that substance, what make up that substance. I give you this heaviness. Let me just use the layman's language. Okay, let me give you an illustration so you understand it. Okay, let me see a beaker with a silver nitrate solution and a graduated cylinder with a potassium chromate solution are placed on a single pound balance. It displays the combined mass of 104.50 grams. Okay, let me do it this way. Okay, so that's 2 Ag NO3 plus K2 Cl2O4 give you Ag2 Cl2O4. Balance the chemical as KNO3 2KNO3. Okay, let's say the total mass here is 104.50 grams Total mass after 104.50 grams. Okay, this is before the reaction and after the reaction. Alright, so this is what the law of conservation of mass is saying. The total mass here is equals to the total mass, because balancing the chemical reaction or this chemical equation, we realize that the same number of particles or elements or substance we have in the reactant side is equal to the same number of products. Two moles of silver, 2 moles of silver, chromate, two each. Oxygen we have 4, okay, 6, 10 on this side, so I have 10 on this side. 2 moles of potassium, 2 moles of potassium. So it's just that's what the law is saying. It's just it's conserving mass. Okay, it doesn't get destroyed. Same thing as the law of conservation of energy. Okay, we also to look at the law of constant composition. Law of constant composition. As a science student, we can think about what this law is trying to say. Law of constant composition. Okay, all samples of a compound have the same composition, the same proportions by mass of the constituent elements. Of all compounds, all samples of a compound have the same composition, the same proportions by mass of the constituent elements. Like given a compound, let me see, water. Okay, all samples of this compound, water, we have water here. Constant composition. Even if we have, let me see, we have 5 grams. Okay, let me use liter. So to make it more accurate, so say 10 liters of water here, and we have 15 liters of water here. Okay, this is not about the mass. It's talking about the composition of the compound. So he's saying all samples of a compound, okay, have the same composition, the same proportions by mass of the constituent elements. Alright, we have 2 moles of water here. We have 1 mole of oxygen. 2 moles of water, 1 mole of oxygen. These compounds have the same elements. We have different volumes here, but their individual masses are the same thing. We have the molar mass of water is 2 grams per mole. So oxygen is 16 grams per mole. 1 mole of water. Yeah, it's the same thing here also. The same thing you find here, the same thing you find here. Okay, it's just constant composition. They don't change. They're not like let me see, like gravity. When you leave the earth and you go to the moon, gravity changes, because gravity on the moon is much more lower than it's on earth. Okay, but here it's different. These compounds have the same composition of elements. Okay, so we move on to Dalton's atomic theory. Dalton's atomic theory. This is most likely the simplest, one of the first theories we get to learn about atoms. Okay, in 1807, I don't give you history, but he published his own philosophy, which he called Dalton's modern atomic theory. Okay, and here we see a bit of the law of conservation of energy in applied to atoms. Okay, because it's the atomic theory. He said matter is composed of tiny particles called atoms, which cannot be created nor destroyed. In other words, he's saying atoms can never be broken down. According to Dalton, atoms cannot be broken down into simpler particles. Atoms can never be broken down into similar particles. To simpler particles. or no, created. Atoms can never be created nor destroyed. Okay, what he's saying is you can't like atoms are just one whole substance or one whole particle. We don't have subatomic particles. We don't have things that can be atoms can be taken from, or things that can make up atoms. Atoms can never be created nor destroyed, because he said atoms are the tiniest particles you ever find, according to Dalton. So it's just trying to give us that illustration of the law of conservation of energy, which apply to atoms. And he said all atoms of the same element are identical. Of course, okay, let me give you this before we go to the second theory. I'll give you the theory, and I'll give you the limit, the what's disproved that theory. Okay, when you go to nuclear chemistry, you realize that you can break down atoms of elements through nuclear energy. We also realize we have in atoms we have protons, we have neutrons, we have electrons. So this is null. Alright. A second theory: atoms of the same elements are identical. Atoms of the same elements are identical. Each atom of a given element has identical attributes. That is, they have the same mass and the same chemical properties. They differ from the atoms of other elements. Okay, atoms of a given chemical element are identical. Okay, let me use this. All atoms of the same elements are identical. Okay. I also said the atoms of the one element is different from the atom of another element. Atoms of one element atoms of one element is different. What he's trying to say is, yes, we have sodium, we have potassium. What he's saying that the atoms in sodium can never be the same thing as atoms of potassium. Okay, and this one is saying all atoms that compose sodium are identical. They are all the same thing. You can't differentiate one from another. Okay, and we talk about what disproved Dalton's theory. Okay, and we also say compounds are made up of more than one kind of elements. Okay, we also say compounds are made up of more than one kind of elements. And in a compound, the ratio of the number of atoms of an element present is either an integer or a simple fraction. Okay, you know that's from law of simple composition or law of multiple proportion. Alright, the ratio of the number of atoms of an element present is either an integer or a simple fraction. Okay, I won't go back to that later. Maybe when we have covered much ground, then I'll go to law of constant composition of simple composition or multiple proportion. Alright, so this Dalton's theory, how can we describe it? Dalton used his imagination, presented in a more detailed description of an atom compared to Democritus. Okay, because he said a chemical reaction involves the separation, combination, rearrangement of atoms. It doesn't result in creation or destruction of atoms. It involves in separation, combination, and rearrangement. In separation, you don't have to destroy anything. Just separate them. You can also bring them together. Rearrangements, you rearrange them from place to place. Two atoms are composed this way. You can rearrange them to compose this way. We can combine them, two different atoms. That's what Dalton said. A chemical reaction involves the separation, rearrangement, and combination of atoms. It doesn't involve creation or destruction. So you can't create atoms or destroy them. You just combine them, you rearrange them, and you separate them. Okay. And we should note that Dalton didn't know what an atom looked like. Okay. He just described it using his imagination, though his work gave birth to the modern era of chemistry. Okay. This theory, it was so good that it's an extension of law of definite proportion. It was so good. It supports the law of multiple proportions as well as the law of conservation of matter, like we discussed earlier. Okay, because law of conservation of matter or mass. All right. So this theory was good, but it had flaws. All right, it had flaws that we find out later when we go to other experiments that we did. Okay, and if you're talking about atoms, atomic theory, you should be able to say what an atom is. How can I describe an atom? Okay, on the basis of Dalton, he said the atom is the smallest unit of an element, that can be involved in a chemical reaction. Based on all these theories, Dalton described an atom as the smallest unit of an element involved in a chemical reaction. Okay, since you can't break it, create it or destroy it. On its basis, it is the smallest unit of an element involved in a chemical reaction. Okay, then we move to, okay, fine. He gave his own basis, his own theory, but series of study begins to show that the atom is not indestructible. As it's not indestructible. It has small particles, subatomic particles, protons, neutrons, and electrons. All right, protons, neutrons, and electrons. After years of study, long after Dalton, we found out that atom contains some small tiny particles. Protons, the neutrons, and the electrons. Let's see. We'll talk about the cathode rays now. The cathode rays. This is more of a discussion because the cathode rays. I'm not going to be drawing all the experiments involved, but just explain them in imaginative detail. Okay. He found out that ordinary pressure gases are electrical insulators, but when subjected to low pressure and high voltage, they break down and conduct electricity, and the glass container begins to glow. The experiment showed that this was caused by bombardment with glass by rays originating from the cathode and travel towards the anode. The cathode is the negative electrode, anode is the positive electrode. Okay, so at low pressure, gases are insulators. Okay, according to experimental results. But when you increase at ordinary pressure, gases are electrical insulators. When you lower the pressure and increase the voltage, increase the current that passes through, you find out that they conduct electricity. The container of the glass, like the cathode ray tube, begins to glow because the particles that move through them They are somehow they are negatively charged.